Okay, so let's take a look at question 5 from the 2011 scholarship paper. So this is 2011 paper, and this is scholarship paper. And we're just going to do question 5, part A in one video, and then I'll do part B in the second video. Part A is all about isomerism in organic compounds. So it's quite cryptic, and you need to take your time and read through this, and then try just to make any notes that you can as you go through reading the paragraph. So I'm going to make some notes as I read through the paragraph, and then I'll open a separate page to structure how to practice drawing these isomers. So compound A has the molecular formula C4H4O4. Not much I can tell from that right now, other than to get all those oxygens in there, all those 4 oxygens, you're going to have either lots of alcohol groups or carboxylic acid groups or aldehyde groups. So they're the main sources of functional groups that you can get lots of oxygens from for level 2, level 3 organic content that you were taught. Compound B is a stereoisomer of compound A. Now, stereoisomerism is not the same as structural isomerism. So structural isomerism is the most basic type of isomerism, where you have the same molecular formula and you just move around the different the position of the bonds. Stereoisomerism is that category which includes geometric. So anytime you see stereoisomerism, you need to think of geometric isomers, or alternatively, it also includes optical isomerism. So that's a bit of a hint, because geometric isomers, they're going to have a carbon-carbon double bond, and then you're going to have 4 different groups attached to those carbons with double bond. So you need to be aware of that. Optical isomerism will have a chiral carbon, and a chiral carbon has 4 different groups attached to it. So there's some information to bear in mind. Now let's move on. The melting points of compound A and compound B are 135 degrees Celsius and 287 degrees Celsius respectively. So the 135 is for compound A and the 287 is for compound B. So compound B, the intermolecular bonding between 2 molecules of compound B is better than the intermolecular bonding between 2 molecules of compound A. This is due to the ability of compound A to form intermolecular hydrogen bonds. And from hydrogen bonding, we know that that's possible if you have an OH group present, which could be just from a straight alcohol, or it could also be from the carboxylic acid oxygen, or the alcohol group on the carboxylic acid. So some hints building at this stage. Compound C is able to exist as an enantiomers. So this means it has a chiral carbon. And compound C is formed by using heat and dilute sulfuric acid with compound A. So this sounds very much like an elimination reaction. And if you eliminate on an alkene, you form an alkane. So we're suggesting that compound C is an alkane of some sort with a chiral carbon, chiral center. And that's its molecular formula right there. We continue. Compound A will react with potassium permanganate, which is an oxidant, strong oxidant or oxidizing agent, to form compound D, with that formula right there. And then compound D is further oxidized by periodate, which is periodate IO4 minus ions, to form compound E. And compound E is the molecular formula C2H2O3. It gives a positive test with Tollens reagent, which immediately tells me it's an aldehyde of some sort. So if compound E is an aldehyde, compound D must be a carboxylic acid, and therefore compound A, to get a carboxylic acid from compound A, then compound A must have had some sort of alcohol group attached to it. So there's another, so what's the part? The question is asking you to identify structures compounds A to E, justify your choice of stereoisomers, so that would be A and D and B, and write a balanced equation for the reaction of compound D with Tollens reagent. So there's quite a lot to this for part A, and as I say, you need to be able to follow all those hints, and you need to read through the entire paragraph and retrospectively think backwards to figure out the starting structures of A and B. So we've gone through all the information. I'm going to start answering this on a separate page. All right, so I've a new page here, and as I've recommended before, you want to have a printed copy of the exam question in front of you as you watch these videos, just to keep track of where I get all this information from. The molecular formula for compounds A and B is C4H4O4, And as usual, as I say to my students when I'm teaching isomers, there's no real systematic way to figure out what the formula is for these compounds other than to just put some of the atoms down on paper and then check how you're going with your structures. But I do know that if we're dealing with geometric isomerism here, then we need to start off with a central double bonded carbon situation. And then to get all these oxygens in here, like I said already, you're going to have to put in a carboxylic acid group. So I'll just draw that like that, and that can get 2 oxygens. And then another carboxylic acid side group will get another 2 oxygens in there. So you've satisfied your 4, and then you just need to put in your 2 hydrogens. It will just check for geometric isomerism. We want to have carbon-carbon double bond, which we have. We want to have 2 different groups on each of those carbons. So we have 2 different groups right there on each of the carbons. So that's compound A. And I'll explain why the cis isomer is compound A in a second. Compound B then is going to be the trans isomer, which is just to simply put those groups on opposite sides. And that's compound B, the trans isomer. It doesn't ask you to name these compounds, and it's not, the names aren't on the NCEA answer schedule, so we don't need to lose time trying to figure out the names of these compounds. But you have the correct structure there with the correct molecular formulae. Now, the reason I know that compound A is this one and compound B is the trans, it's to do with the melting point information that you were given. So the melting point for A is 135 degrees Celsius, and the melting point for B is 287 degrees Celsius. And this is because compound B, if you think about it, you have a situation where this molecule can be represented like this. And therefore, because this is quite a bulky side group right here, so these molecules can slot into each other, one molecule into another like that. So the first thing is the spatial arrangement. The molecules can get close together. And then the second thing is with the carboxylic acid side group there, you can get intermolecular bonding both in the forwards direction and in the reverse direction. So this way and this way. Whereas if you put 2 molecules of compound A together, well, first of all, the situation is that they're arranged like this, which makes them harder to get close together spatially. If we're dealing with this large side group here, the hydrogens are quite negligent, they're so small. And then you can only get bonding in this direction. So the molecules, the main thing is in the NCEA answer, they talk about the only being a possibility of 1 hydrogen bond forming with molecule 2 molecules of A together, but in the reality, both of these molecules can form hydrogen bonds with 2 times. It's more about spatial arrangement and getting those molecules close enough together to make those bonds of that contact. So that's why the melting point is higher for compound B, and that's why it's the trans isomer. Now we've identified successfully compound A, and compound A, we then need to talk about what happens next. So if I read on with the question, compound A reacts on heating with dilute sulfuric acid to form compound C. So we're just going to move down our page here a bit. And so we have compound A. So it reacts with dilute sulfuric acid, so H2SO4, aqueous, and heat. And this is an elimination reaction. So we're going to eliminate that carbon-carbon double bond, and it forms compound C, which has a chiral carbon. So the compound here we're looking for, we don't touch the carboxylic acid groups. They stay where they are. The double bond is broken, so now we just have a single bond. The 2 hydrogens, we're returning a hydrogen from the sulfuric acid supplies those extra hydrogens. And then to make this a chiral carbon, we must have an OH group on there. And that makes that a chiral center because it has 1, 2, 3, and 4 different side groups. And that's the criteria for an antimeric isomerism. So that's compound C because it has the molecular formula C4H6O5. So 1, 4, 3, 4, 5 oxygens, and then everything else should be there if you check it. The next thing that we can also talk about then for compound A will react with potassium permanganate to form compound D. So compound A, we can also react that with potassium permanganate, which is an oxidant. And oxidant will form, oxidation of an alkene will form a diol. And therefore the compound here we get is, just use a different color now, not to mix these things up. So you have your double bond is now broken. The double bond is broken, and instead you get a this carboxylic acid groups aren't touched. You can't further oxidize the carboxylic acid group, but your OH adds on there, and then your hydrogens are still up there. So this is your diol situation. And then that's compound, that should be compound D. And the molecular formula for compound D is C4H6O6. Okay, so that's compound D. Then we read on. When compound D is oxidized by periodate ions, compound E is produced. Compound D has the molecular formula C2H2O3 and gives a positive test for Tollens reagent, which is the giveaway that it's an aldehyde. And each molecule of compound D produces 2 of E. So this molecule is going to split up and give us 2 of E when there's oxidation with iodate, which is IO4 minus. Okay, so what we get here now is we get oxidation of the OH groups here, further oxidation of the OH groups to form aldehydes. So we have our carbon still bonded to the carboxylic acid group. We have one hydrogen, which was from here, and then the OH group, this OH group is further oxidized by the iodate to form the carbonyl carbon to oxygen. And then there's a split through the molecule of D, and then we get the same situation happening on the other side. So we get our carbon double bonded or to the carboxylic acid hydrogen right there, and then we get your carbonyl carbon introduced. So this is compound E, and that is the molecular formula of C2H2O3. So they are aldehydes. That's an aldehyde. Okay. The next thing they talk about then is they take compound D and they test it with Tollens reagent or ammoniacal silver nitrate, and each molecule of compound, so then they just want you to write down the balanced equation for the reaction of compound D with Tollens reagent. Now Tollens reagent, I just looked this up just for a good definition. You would have done this in school with your level 3 chemistry. It gives you that nice silver mirror, a nice experiment. So Tollens reagent is not commercially available due to its short shelf life, and therefore this is why you end up making it in the school lab. What you do first of all is you get silver nitrate, AgNO3 aqueous, and add a few drops of dilute sodium hydroxide. This gives you Ag2O silver oxide, which is brown. It's a brown precipitate. And then you take the brown precipitate, this silver oxide, and you dissolve it in aqueous ammonia, and then you form this silver ammonia complex ion, which you would remember from level 2 when you were doing your complex ions. So that has the formula AgNH32 and plus 1. And then what you do is, well, you react this stuff in the presence of sodium hydroxide with your aldehyde. So the equation, the simplified equation for this is you take your aldehyde, which is just right here, we just had it, and then you're adding silver ions from this complex, and then hydroxide because you added the dilute hydroxide, and then you get your further oxidation of your aldehyde. This is your aldehyde, and then you form the carboxylic acid group instead. Carboxylic acid, this is further oxidation. So you have a dicarboxylic acid there essentially. Then you get solid silver, which gives it the silver mirror, plus water, And because you have an imbalance in the oxygens on either side there, just need to highlight this. So you have three, four oxygens there, and then you have 3, 4, and 5 oxygens here. What you need to do is you need to add a 2 here, and then 2 for the silver, because they need to deal with the hydroxide as well. So that's your equation for your reaction with Tollin's reagent. And that's the answer to question A, part 1. We're just going to do question A, part 2, because it follows nicely from this one. Okay, so the second part of question 5, part A, draw 2 other isomers of compound A, one that has different functional groups from compound A, and another that has the same functional groups as compound A. Explain why neither of these isomers meet the requirements to be compound A as described in part A. Okay, so you need to do a little bit of drawing with your atoms, but the molecular formula for compound A, remember, is C4H4O4. And originally I drew one compound, it wasn't correct. I got one of them correct and then had to take a look at the answers for the other one. The one I drew was, I basically took compound A, which was originally this situation. So that was compound A, the correct one. And what I did was I just removed this double bond over here, and I formed this situation where you have 2 hydrogens on that end, you have a carboxylic acid group here, and then you have the carboxylic acid group here. And of course, this doesn't fulfill the requirements for geometric isomerism, because you have 2 groups which are the same on that carbon, and you have 2 groups which are the same on that carbon right there. So no geometric isomerism possible. So that's why that compound isn't allowed. The other possible compound to draw, and I had to look this one up, was this dialdehyde situation, essentially. So you have 2 aldehyde groups, that's CHO right there. And the problem with that group is that if you pick that compound for compound A, and then when you oxidize that, you'll end up forming a compound which has 2 carboxylic acid groups on either of the carbons, basically a 4 carboxylic acid compound, which is not D, because you cannot then undergo further oxidation. There's no further oxidation possible. And so you couldn't form your 2 aldehydes from that. Not possible. So let's take a look just at the answer for that in NCEA, from the NCEA guys. So let's just go down and take a look at the final part there. Other possible structures of A. So they're the 2 structures. They look a bit different from the way I've drawn them, but you can check them for yourself. They're the exact same. So reasons these structures are not selected. So this compound here, this one, number 1, has alcohol and aldehyde functional groups, so would give a product with 4 acid groups, 4 carboxylic acid groups, which are just true for you, when reacted with potassium permanganate, so will not match the formula given for compound D. Number 2 has a double bond at the end of the chain, so when reacted with sulfuric acid to form a compound, the resulting product will not have enantiomers. That's correct as well. So the situation we're talking about here is if we break that double bond, we'll get a situation where we have a carbon, a carbon with carboxylic acid group there, and a carboxylic acid group there, and a hydrogen right there. So this is not a chiral carbon situation. There's 3 groups the same there, and this carbon has 2 groups the same there. So an enantiomer is not possible. So that's your answer anyway for question 5, part A, and we'll do a separate video for part B.